Okay, welcome to Unit 22. We talk about improper integrals. So there are two possibilities to have improper integrals. Either we have an infinite region, or we have a function, an unbounded function. So an example of the first type is if we integrate, say, from 3 to infinity e to the minus x dx. So that's an infinite region, right? And or another possibility is if you integrate from minus 3 to 3, 1 over x to the 5 dx, that would be an infinite. The function is unbounded. So this is maybe type A, this is type B, this is of the type A, and this is of the type B. But it can be even of both. For example, of this, if you have this 1 over x squared dx. So this is A and B. So that's improper integral. Improper, it's just, not always clear whether the integral really works or not. So we have to be careful about it. For example, I take the integral from, so the example A is I integrate from 1 to infinity 1 over x squared dx. What we usually do is we approximate this by a finite integral. So this is a limit when b goes to infinity, and we go from 1 to b 1 over x squared dx. And in this case, there's no problem because we integrate from 1 to b. We know how to integrate that. So that's the limit b goes to infinity. And then we have minus 1 over x from 1 to b, which is the limit b goes to infinity. And then we put b, so we get 1 minus 1 over b. And that actually works well in this case. If b goes to infinity, that goes to infinity, then this goes to 0. For b goes to infinity, so that is equal to 1. So we have actually got a situation where we have a infinite region. Just plot this with a different pen here. So this is 1 over x squared. So we integrate it from 1 to infinity here. So we have computed the area of this thing. So this area here is equal to 1. Pretty cool. Now, if we take another example, let me just take the example when we take the integral from 1 to infinity 1 over square root of x dx. So in this case, that also goes to 0. 1 over square root x goes also to 0, but it's again the same thing. I'm not going through all the details, but we have the antiderivative as 1 over square root of x is 2 times square root of x. Square root of x from 1 to b. And in this case, this is equal to 2b minus 2. So what happens when b is going to infinity? 2 times square root of b minus 2, so that goes to infinity for b goes to infinity. So in this case, we have a situation. We have still a situation. I have to get more paper here. We have still a situation where the function looks like this. So in this case, the function looks again like this: 1 over square root of x. It also goes to 0, but it goes less fast to 0, and actually we get an infinite area. Cool. So I want to tell you about the shock. When I learned this, I was completely shocked about this. So let me just show you the example. So what we do is we take the following improper integral. The function is 1 over x squared, and what I'm doing, I'm just integrating from say minus 2 to 2. So I have this function which is here 1/2 goes to infinity, that, so we have that area here. Let's compute that area. So what is the area? And let's just compute it. So we have the integral from minus 2 to 2. That's a nice thing, 1 over x squared dx. We know the antiderivative is minus 1 over x. We go from minus 2 to 2. That's, we can evaluate this at both places, so that's minus 1/2 minus, we take minus here, so we take minus 1/2, but we take minus, minus, so it's again minus 1/2, so this is equal to minus 1. So the area is minus 1. Now, why did it shock me? Because you would think, oh, yeah, maybe it is infinite, so would you actually expect this to be infinite? But you would not expect an area minus 1, because this function is positive everywhere. So how can it be minus 1? And so you can analyze this by actually doing the integral from I showed that last year in a video. Maybe I'm not repeating that. We're going just from t to 2 and then from minus 2 to t. So if we look at that and we compute that area here, I will discuss this maybe more in class. And so then you can kind of see what is the how do we solve this riddle. So that's the thing. I want to tell about something else, which is kind of my favorite example of a improper integral. It's the Gabriel's trumpet. And then we wrap it up because it's such a beautiful day. So we have the following surface. So this is a surface which starts at x equal to 1 and goes to x equal to infinity. We have looked at volumes, right? So, and what we are looking at is so 1 over x is the radius. So we have learned how to compute the area of this, and let's just go not to infinity, but let's go to b and just see what is the area. First of all, what is the volume of this? This is pi over r square, which is pi over x square, and the volume will be then just pi over x squared dx. So the volume, if we compute the volume, what we get with the volume is the integral from 1 to b pi over x squared dx. So this is minus pi over x evaluated from 1 to b. We have just computed that before. So this is pi minus, so we have minus 1 minus b, minus 1 over b, minus pi over b. And for b goes to infinity, this goes to pi. This whole thing here goes to pi. So the result of the trumpet has finite volume. So we have the same thing for the surface area. I just plot that again. So we go again from 1 to b. And when we are looking at the surface area, what we have to do, maybe I'll just make this green. Surface area here, we can approximate this. We make it a little bit bigger by taking the surface area of this cylinder here, so this cylinder mantle here. So what it is, so we have the length of this strip is 2 pi r, which is 2 pi over x, and that's dx. So that area here is 2 pi over x. So what we have is when we integrate from 1 to b, so the area is bigger or equal to integral from 1 over b 2 pi over x dx, which is 2 pi, and then we have log x, the natural log x from 1 to b, which is 2 pi log b minus 2 pi log 1. So that's 2 pi log b, and that goes to infinity. So it has infinite surface area. That's very, very vexing. And the story is told usually like this. So what we have is we can fill what we can do is we can fill the trumpet with pi amount of paint, less than 1 gallon, but we cannot paint it. And as in the last video, I will explain you also, we are not doing that here, that if you take a trumpet which has 1 centimeter here, and you want this to be the whole area, you want to be the area of that piece of paper here. You ask yourself, how high does the trumpet have to be? And the surprising thing is it doesn't fit in our universe. So this area goes to infinity very, very, very slowly. So that's the story of the Gabriel trumpet. And I see you tomorrow.